Actually, there are some times where you actually get that arrow up top, and what that means is if you have an arrow that goes both ways, what that means is sometimes you actually get a reaction where the reactants turn into the products, and then the products become the reactants, and the reaction kind of forces its way back again, and you get this cycle of looping. And I mentioned that that exists, and then I didn't really do anything with that. Now, there was a demo that I've wanted to do for a really long time. And when we got to this part, I decided that this was going to be a good time to do it. Unfortunately, we had to make a bunch of the chemicals, and so I couldn't do it for you on the day that we actually talked about this. And then we went ahead and we did the lab. So I'm going to, Christy, the lady who perhaps you've seen in the lab, in and around the lab before, was actually able to make us the stuff that we needed so that I can demonstrate what I meant by this right now. So I want to do for you guys kind of a cool little reaction, one demo that I've always wanted to do. I did it for the first time for the block this morning, and it worked really well. So hopefully it works for you guys. What I'm going to need is for the four of you to leave your stuff and just take your chairs and slide back a little bit. Because while this isn't the most dangerous thing I've ever done in the lab or outside of the lab, it isn't entirely safe. So take you guys to slide back a little bit. So here's what we're going to do. I'll show you on the screen what this is, and then I'll demonstrate for you guys the reaction itself. So, this is the way the reaction's written. There's a lot going on here. There's four in your notes, what I gave you a simple one. I said reactant A plus reactant B gives you products C and D. In this one, you've actually got reactants A, B, C, and D. This is iodine trioxide. This is H2O2 hydrogen peroxide. This guy here is a starch molecule. And we've got some hydrogen ions. These four things are going to react in these 1, 2, 3 liquids here. And it's going to produce this thing, a starch iodine compound, oxygen gas, and water. And so this thing you're actually going to see there's going to be bubbles that form in this thing. But the cool thing about the reaction that I'm going to do is there is kind of an intermediate step that happens, and the intermediate step kind of looks like this. There's this one here that happens. I have 3. So this guy, and this guy react first to produce these 3 things. Iodine and hydroxide. That's not really what it is. That's actually not what it's called. Well, another name for it is hypoiode is acid. That's an acid. Oxygen gas and water. And then this piece is going to react with this piece to produce these 2. So breaking up the reaction. But in the process of that happening, as these guys build up, it actually forces the reaction to go back and break apart and form these guys again. But then as these guys are going to build up, this comes back. So this is called the Briggs-Rocher reaction. Sometimes it's called the Briggs-Rocher clock. And you'll see why here in a moment. So here we go. Let's demonstrate a reaction that goes kind of a few different ways. Okay, so I've got A and I've got B. A is a clear, colorless solution. And I'm going to fill it up. 200 mils. 100 mils. I know what Dylan, are we okay? Good. This guy, we're going to use 200 mils of this guy as well. I have 200 mils. So this guy was clear. This guy's a little murky. This guy should be clear. The reason this is murky is because that guy didn't totally dissolve. That's okay, the reaction's not working. A in there. For compound for solution B in there. Make this thing really interesting. We're going to add solution C. This is the dangerous one. What's going on? Nothing? Okay, so first one was colorless and clear. Second one was, it's white and kind of murky. This guy is colorless and clear as well. This is hydrogen peroxide. This is this guy here. Before I pour it in, I'm going to get this thing stirring. Come on. There we go. Okay. Here we go. So often. There we go. We'll watch it for a second, and then we'll talk about it. And so this is an example of a reaction that's going to continually flow back and forth as the different products, as the different reactants form different products, and those products then become different reactants, and the thing's going to start to loop. And this color is going to get, as it goes, this color is going to actually get darker. So there's a lot that's going on here. There's a lot that's going on here. The first reaction is the reaction of these three pieces to produce this. But as this guy here, this HOI, is getting produced, there's an in-between step where pure iodine shows up, I2, bonds with itself for a brief moment before this acid gets produced. And that's what's giving that yellow color. So as that guy, it'll go clear again, it'll turn yellow, that's the in-between step where the iodine shows up. And then the iodine starts to react, turns into an acid, and then turns into this. This is what gives that blue color. What you can see here, if you look really, really closely, you can see that there's bubbles in the mixture. What's being produced in this step here is a bunch of oxygen gas. So this reaction can't actually go on forever because as the oxygen continually is produced, it leaves the solution. And so the reaction that's happening here is actually going to slow down because this product, which is necessary for this step, or the part that goes back to make the hydrogen peroxide, we lose this. We're just going to pour water. Comments, questions, concerns about what you're seeing. It's a cool little reaction. It serves no real purpose in products. That's a really good question. That would be really dangerous to do. Because any reaction that produces a gas that you seal is going to increase it. Theoretically, yes, but you need something that's really highly pressurized. If I did that, if I did it in a flask and I capped the flask, it could, well, first it would pop the stopper up and actually break the flask. I've never seen that done. It would likely last longer than the short ones. Any other questions about what you're seeing? So there's all sorts of things in chemistry that exist just because they're cool. This reaction doesn't really serve any purpose. It bounces back and forth. It's something that science teachers like to do for their students. I just want to do it before it's a cool reaction. I'd seen it in high school. I saw it again in chemistry at university. And it's a cool example of a reaction that does kind of cycle through. There's another one that we don't have the materials for that our lab tech Yeah, see now it's getting better. That our lab tech really wants to do. And it's similar to this. If you let it starts orange, and if you let the reaction run, it slowly fades into a light blue color. And if she gets the equipment or she gets the chemical, we'll do it for you guys. And the other class asked the question, you guys haven't, why it constantly needs to be stirred. And the reason this guy needs to be stirred is because the reaction's happening kind of at different points throughout that liquid. And so the concentrations of different compounds and ions are going to be different in different places. Constantly mixing it is going to make it so that those are always uniformly distributed, and it's going to allow this guy to happen faster. So the other reaction that does something similar to this, if we just, so I've seen it done on a Pyrex sheet, like a glass baking sheet. If you do it on a glass baking sheet, the the chemicals start orange, and they slowly fade to like this color. How they fade is really cool, and so I'll show you guys that. If we get the chemical, I'll show it to you. But it fades to kind of a light blue, and then it stays there. You take the baking sheet and then give it a big shake. It remixes everything, quickly turns back orange, and will slowly fade to blue again. Shake it again, and it'll keep going back and forth. As this guy progresses, because this guy leaves, eventually there's not going to be enough oxygen present. Eventually there's not going to be enough oxygen present to keep this guy in solution. And what's going to happen is this guy will eventually introduce a fourth color, purple, which is a really pretty purple. But in chemistry, if you ever see a purple gas, purple gases are very dangerous, all of them. And so this one it will in a second produce a purple gas. And that is pure iodine, evaporating off of this. Iodine on its own is quite toxic. So when that happens, that's when I have to stop the reaction. But until that happens, you can just see. Yeah, comments, questions, concerns about this thing? Okay. Yeah. No, that's not a scale. That's what's stirring. So that is a magnetic. So to stir things uniformly in chemistry for things especially that are dangerous, I want to be over here. I don't want to be standing over top of that thing stirring it. So there's actually the little white. If you saw it, there's a little white thing at the bottom of that beaker before I put the chemicals in there. That little white thing is a magnetic rod, and so that plate is designed to put the thing on top. There's a dial on the front that I can change the magnet inside that spins at whatever speed I set it to. And so when the magnet spins underneath that white shield, the white stir rod, the magnetic rod that I put inside, spins inside the thing and causes it to stir. There are stirring ones that also heat, so it can be a heating pad as well, but it's not stirring. There's another demonstration I'll use this stuff for you guys. We might do it before spring break. We might have to do it when we come back from spring break. That will use the stir rod or the stirrer for again. There it is. Can you see the purple gas forming? All of a sudden it just shows up. So that guy. Let's see it go. And so at this stage, this is effectively going to kill the reaction. Because the thing I'm adding here is called sodium thiosulfate. And what it does is it's going to pull out, and it's called purple. It pulls out all of the iodine ions and turns them into an iodide compound. I don't want that purple gas. Now we get it up. So what you see coming off there isn't the gas, it's actually steam. It's water vapor. There we go. The reaction of this with the iodine in here, this is actually quite a warm reaction. If anyone else is going to touch it, you won't. So these guys were at room temperature. And that reaction is actually not quite hot. And that is not a hot plate, that's just a stir. It's just stirring what's there. Oh. It's taking a lot longer to calm down than the last one. Come on. You can do it. You can do the thing. Figure yourself out. There we go. And eventually, once that bluish color disappears, then we can do that. Cool. Come on, you. Undo that. Okay, done. There we go. So that's the Briggs-Rusher reaction, also called the Briggs-Rusher clock. An example of, it's something, I'm just looking, I look for excuses to show you guys cool stuff. I think this is a cool demo. Just a simple example of a reaction that goes, flows back and forth. You can make, there are other reactions that do this, they're a lot less interesting. Some of the reactions will be two reactants, two products. It'll push it one way and then it'll stop. You can heat it to force the reaction back, and then turn off the heat, let it cool, and the cooling process kind of forces it back the other way too. This is a lot more dramatic an example of a reaction. So yeah, it's done. Now that it's not turning blue again, we can move on. Any other comments, questions, concerns? I'm just going to let this thing sit over next to my desk. You guys can solve that. I'll let that cool down. Sweet. Okay. Sweet. Okay, so you guys, we made it a lot further than we made it with the other class last day. So you've seen a bunch of this stuff already. So let's move ahead to where we were. This is where we were. Boom. We were in the process of talking about this. Balanced chemical equations. So you recall, you can stay on this page. I'll flip back here briefly. Just to kind of summarize where we were a couple days ago, because it's been a couple days and you've been in the lab since. Chemical equations use words or symbols to give us a picture of what's going on. As you can see with the Briggs-Rosher chemical equation, excuse me, there was a lot there. We had 4 reactants, we had 3 products, and then that thing starts to loop. It gets cumbersome to start or to use names, to use words for that. It becomes, well, it's wordy. It's a lot longer, and so we don't want to do that. As much as possible, we want to use formulas because it starts to condense this thing. So then I introduced to you guys the concept of the skeleton equation, and this was the example for the skeleton equation that I used down here. Mg plus O2 produced MgO, and then we looked at this and we said, okay, this clearly tells us what's going on. This tells us that magnesium is going to react with oxygen. It's going to produce MgO. But then we looked at this thing and we said, okay, well, yeah, we know that it's going to do that. And we know that MgO is going to form because we've got Mg has a charge of +2, O's got a charge of -2. The rule for ionic compounds is that when they react to balance each other's charges. And they want to do that in lowest terms. So you'll need 1 +2, 1 -2. Those are going to come together, create this compound, and you're done. But we went ahead and we counted these things. We said, okay, well, this is just 1 atom of magnesium. This guy here, O2, is 1 molecule of oxygen. That molecule of oxygen has 2 oxygen atoms in it. And this compound that gets produced, MgO, has 1 magnesium, 1 magnesium atom, 1 oxygen atom. So this thing is unbalanced. It does not obey the law of conservation of mass, which is what your lab looked at over the last couple days, because it doesn't have the same amount of oxygens on both sides. And so what we want to do is we want to take our skeleton equation. The skeleton equation is good for giving us an idea of what's going on. But we want to take that skeleton equation and we say, okay, an idea is a good place to start, but I want more than an idea. I want exact quantities of what's going to be produced here. And so that's where I went ahead and we introduced this idea of having a balanced chemical equation. According to the law of conservation of mass, atoms can't be created or destroyed in a chemical reaction. In physics, we can destroy atoms, we can create atoms, it gets complicated. But in chemistry, as far as these reactions go, when they come together and they react, things just get moved around. Nothing gets created, nothing gets destroyed. Sometimes energy is produced, like you saw that thing got hot. But as a general rule, the atoms that are there at the beginning need to be present there at the end. They might be connected to something different, but they're going to be present. So when you go ahead and you balance these things, in a balanced chemical reaction, the same number of atoms of each element must be present on both sides of the arrow. And I gave you this example down here. This is the thing that we were in the process of talking about. This guy here says, okay, well, I've got, if you recall, I'm going to write it down here so that it's easy to refer to. The original equation, the skeleton equation, was Mg plus O2 arrow, or reacts to produce MgO. That was the skeleton equation I gave you on the previous page. You say, okay, well, this thing wasn't balanced. It's a skeleton equation. I've got 1 magnesium here, I've got 1 magnesium here, but I've got 2 oxygens on the left and only 1 oxygen on the right. And we know that this is how they show up because of the Lewis dot diagrams we did for things like oxygen. Said, well, each individual oxygen wants to gather to itself more electrons. It's got space for 2, and so when it buddies up with another oxygen, who also wants to take. Those two then are allowed to share. They create a molecule of oxygen. I'm going to call this is one molecule of oxygen. And that one molecule of oxygen, the covalently bonded oxygen atoms, that one molecule has two atoms of oxygen, and they are covalently bonded. I connected it to stuff that you'd studied in Math 9 when you guys were looking at equations. We talked about how the numbers out front of a variable in an equation is called a coefficient, and it tells you how many you have of a particular variable. So here, with that 2 out front here, that coefficient means I have 2 atoms of magnesium. This means I've got 2 separate magnesium oxide compounds. When there is no coefficient listed in math, it'll be the same as it is in chemistry. When there's no coefficient listed, what is the number that's assumed to be there? 1. So we often don't list them, but you can. When there's no coefficient listed, that means there's a 1 there, so that this O2 represents a single molecule of oxygen gas, and that single molecule has 2 oxygen atoms in it. So this blank right here, this is achieved by using blank in the front of each element. That is where we're going to put the word coefficient. And it's actually going to be plural. This is achieved by using coefficients in the front of the elements and compounds present in the reaction. Now you've got to be deliberate about where you put these coefficients. Just like in math, the coefficients always go out front of the letters. So here, here, and here is where we'll place these things. I have seen students try and place coefficients in between things. You can't break up compounds that exist. We know MgO is MgO. You can't force numbers in between where numbers do not belong. The other piece of information that shows up in a full-on, as detailed as it gets, balanced equation are these letters here, and I want to address them because I'm sure you've noticed them, but we perhaps have not seen them before. If you see at the end of a formula for a chemical a letter in brackets, these letters, S, G, and there's actually a couple other ones, L and AQ, these letters just tell you what state, excuse me, what state these different elements are in. So this Mg with a bracket S afterwards tells you that when this reaction occurs, this magnesium is S, it's a solid. And we've got magnesium solids in the lab. It's something you're going to do a lab with it. It's a ribbon of, you have already actually. On that very first day, you took a strip of magnesium ribbon, a little chunk of it, and you reacted it with hydrogen or hydrochloric acid. The very first lab that you did, you played with pure magnesium. You reacted it with something different, but on its own, magnesium solid wrapped up in the lab is going to react with the oxygen in the air. It's going to produce MgO. This type of reaction has a kind of a common name, which you know already, kind of in a different form. If this wasn't magnesium metal, if it was instead an iron compound, it was iron metal, what do we call it when iron metal reacts with oxygen to produce iron oxide? Somewhat louder. Yeah, I heard it. You said it. Say it louder. We call it rust. So that is the process of rusting. In iron, it produces kind of that deep red, kind of crumbly compound, iron oxide. But this is the exact same procedure. You have a metal reacting with oxygen, producing a metal oxide. This is the process in which magnesium rusts. And all sorts of metals do this kind of on their own. If you guys have parents or an aunt, sometimes it's an aunt and uncle. For me, it was my grandma. She had literal silverware, spoons, knives, forks made of actual silver. Has any of you seen this? You've had a relative who've had this, a couple of you? What does that silverware do when you just leave it? Do you know? Have you seen it? Did your grandma ever make you polish it? Or whoever it was? Dennis, did you have to polish it ever? Your mom did. Okay. The reason you have to polish it is because silverware on its own it's silver. It's Ag. There's nothing beyond that. It's pure silver. But if you let it sit in the air, that metal is going to react with the oxygen on the air, and you're going to get a fine layer over top. As it sits for a while, it starts to kind of turn black. If any of you have silver jewelry, it does the same thing. It starts to fade, and if you let it go long enough, it starts to blacken. And so Dennis's mom has to then go around and polish it. And the act of polishing it wipes off that layer of black, revealing the silver underneath. That layer of black is actually silver oxide. So in the act of polishing it, you're actually wiping away the silver that's reacted with the oxygen, and you're actually decreasing the amount of silver that's there. So over time, the act of polishing silverware will actually make that silverware shrink because you're getting rid of this compound. So this is a reaction that you've seen perhaps before. All gold does this as well. If you have gold jewelry that starts to dull, that you then want to polish up, that's what's happening there. So, a relatively common reaction. You're just used to seeing it with a different metal instead of magnesium. And this is as far as we got when we were talking about balanced equations. So let's actually go ahead and figure out how we go about balancing these things. We're going to do a quick review of counting atoms because so much of balancing involves some basic counting, and the counting isn't actually quite so basic. So up here we had coefficients out front and we had subscripts inside. I want to focus in on this guy here for a second. The way I had you guys write this down, or I wrote it down, and whether or not you copied it, well, you did or didn't. We had a 1 out front here. That 1 represented the molecule, and that subscript there too told us how many oxygens were present in that 1 molecule of oxygen gas. So if I go ahead and I look at this example here, I've got 5 as the coefficient out front of the H2O. H2O you should all be familiar with, it's water. In a water molecule, you should be familiar with the idea that a single molecule of water has 2 hydrogen atoms in it and 1 oxygen atom. When there is no subscript listed, that number is assumed to be a 1. So this is kind of a nice little simple example to get us started counting atoms. If you have just a single H2O, all you've got there is 2 hydrogens and 1 oxygen inside that molecule. If I toss a 5 out front, how many hydrogen atoms do I have now? That 5 out front means I've now got 5 molecules of water. Each water molecule had 2 hydrogen atoms. So 5 molecules of water must then have how many hydrogen atoms? Yes, it's got to have 10. I have 5 groups of 2 groups of hydrogen. So we've got a mathematical operator that does this for us. How did you get 10? Or 2 hydrogens. You have 5 pairs of 2. So what mathematical operation are we doing with 5 pairs of 2? 5 times 2. We're multiplying them together. You multiply the coefficients by the subscripts, and it tells you how much you have of each. So I'm going to jump to this guy over here. There are 5 groups of 2 hydrogens, so 5 times 2 is going to give us 10 hydrogen atoms. Here's what we did. That coefficient out front is this first blank here. That 5 describes the amount of molecules present, and the subscripts, however many there are, describe the number of atoms of the element that's directly in front of them. So that 2 is connected to the hydrogen. There is no subscript on the O, which means we assume the subscript is 1, and it is directly on the oxygen. So then to figure out the number of hydrogens, we just said we had 5 groups of 2, so that's 5 times 2. 5 times 2 is 10. If the mental math isn't there, you can use a calculator. I don't care. You can finger count. This isn't a math class, this is a science class. I just need you to be able to multiply small numbers. 5 groups of 2 is 5 times 2, 10 hydrogen atoms. And then if each water molecule has 1 oxygen, and I've got 5 molecules, 5 times 1 is going to just be 5 oxygen atoms present in 5 molecules of water. That's a really relatively simple one. Let's make it more interesting. So let's look at this compound here. I've got Ca3PO42. Ignore the 5 for a second. That compound is calcium phosphate, and I want to review where that compound came from. The reason calcium phosphate is Ca3PO42 is because when calcium, and gentlemen, are we on our phone over there? We are on our phone. Put your phone away, Michael. What is so important we can't watch it later? Is there a soccer game on right now I don't know about? No, soccer's wildly interesting. Trying to teach every 4 years? Yeah, trying to teach every 4 years is really quite difficult because World Cup is on, and I have students watching it all over the class. I digress. I've got calcium phosphate, Ca3PO4 in brackets 2. Why? Well, because if you recall, calcium has a charge of +2, and phosphate, this thing here, PO4, has a charge of -3. When you make an ionic compound, ionic compounds react in such a way that you have charges balancing each other. We want the number of positive charges to equal the number of negative charges, and we want them to do it in lowest terms. So when I go ahead and I make calcium phosphate, if calcium is bringing a +2 charge and phosphate is bringing a -3 charge, what's the smallest number that 2 and 3 both go into? 6. So how many groups of 2 am I going to need to give me +6 charge? I need 3 of them. How many groups of the -3 phosphate am I going to need to give me, I'm going to need 2. To give me that -6 charge, I'm going to need a 2 here. And when you bring the entire group of a polyatomic ion, you need to throw brackets around the polyatomic ion and then put the subscript out back. So just a quick review of what we did a couple weeks ago. So the reason that calcium phosphate is Ca3PO42 is that we're trying to balance out these charges, and now once these charges have been balanced, you are not allowed to change this thing. So I've got 3 groups of calcium, and I've got 2 groups of PO4. Each group of PO4 had 1 phosphorus, and each group of PO4 had 4 oxygens. So if I just cover up the 5 for a second, and I look at what I have here, this means that a single compound of calcium phosphate has how many calciums? 3. How many phosphates? I have 2 groups of PO4, and each PO4 had 1. So if I have 2 groups of PO4, how many phosphoruses do I have now? I've got 2 phosphoruses, and how many oxygens do I have if I have 2 groups of phosphate? I've got 8. I multiplied these two, or you guys just now, I think it was Luca said it first, multiplied these 2 subscripts together. Was it not Luca? Nope. Okay. Sorry, then it must have been Josiah. No, he denies. Okay. So let's make it interesting. Let's say instead I've got 5. I have 5 groups of calcium phosphate. How many calciums are present there total? 15. I take the coefficient out front. I multiply the subscript on the calcium. So 5 times 3 equals 15 calciums. To figure out the phosphates, I have to do more than that. I take the number of phosphorus inside the phosphate, 1. I multiply it by how many phosphate groups I have, 2. 1 times 2 is 2. And then I multiply it by how many of the compound I have total. So I have the 1 on the inside times the 2 on the outside times the 5 groups present. How many phosphorus atoms do I have in this? I have 10. How many oxygen atoms are present in 5 of calcium phosphate? Each phosphate has 4, and I have 2 groups of phosphate. So that's going to be 4 times 2 is 8. But now I've got 5 of these calcium phosphate groups. So the 8 oxygens there are going to multiply with the 5, giving us 40. So I did 4 times 2 times 5. 4 times 2 is 8, times 5 is 40 oxygen atoms present. When you're ready, flip the page, if you haven't already. And as always, please stop me and ask questions if you have them. Okay, here we go. So ideally we want these equations to be balanced. I'll give you kind of a taste of what's to come. The reason we want these, because we're not going to get there this year, but the reason we want these things balanced, and the reason we spend so much time balancing them now in grade 10, is because next year when you hit Chem 11, depending on who your teacher is, I know if you have Mr. Easton loves to do a bunch of labs. I'm pretty sure Mr. O does as well. So if you have Easton or O, they like to get you guys in the lab doing actual chemistry. And when you start to react these things together, we care about how the balancing works because we want to know what's actually going to be produced. For example here, if I take hydrogen on its own is going to bond with another hydrogen, it's going to make H2. If I take some pure hydrogen and I take some pure oxygen and I react those gases together, it's going to make water, but how much water? You want to know what comes out the other end. And so part of what you're going to do next year, if you decide to take chemistry, grade 11, grade 12, one of the cool things you get to do is you actually get to make these predictions. You say, okay, this is how I think it should be balanced. I'm going to give you some balancing techniques. We're going to practice it a whole bunch this year. Next year, you get to take it into a lab. I think it's going to make this much. And then you actually get to go into the lab and play with it. If I react this much hydrogen that I predicted to react with this much oxygen that I predicted, and I force them together, you're going to actually get to see if your prediction over here was correct. The amount of water that was produced is equal to what you expected it to be. So at this stage, unfortunately, we can't do it to that degree, but we do the practice now so we actually go ahead and do the chemistry next year. So to balance a chemical equation, you start with the skeleton equation, and then what we're going to do is we are going to add and change coefficients. And we're going to do this. We're going to tweak these numbers until we have the same type of each atom on both sides of the equation. So let's take a look at this first one. It's a simple reaction. I'm going to draw a vertical line down from the arrow to separate the left side of the equation from the right side of the equation. And then on each side of the equation, I'm going to list all of the atoms that are present. On the left-hand side, I've got hydrogens and I've got oxygens. They are separate. On the right-hand side, I still have hydrogens and I still have oxygens. They're bonded together into the molecule we call water, but we have these individual pieces and I'm going to count them separately. And then before we do any balancing, what we're going to do is we're going to count, just see how much we have of each piece, which is why we did that counting practice just on the previous page. How many hydrogens do I have as it's written right now on the left-hand side? I have 2. How many oxygens do I have on the left-hand side as it's written right now? I have 2. There's no coefficients in here, so we can assume that those numbers are 1s. 1 times 2 and 1 times 2 are both 2. In my water molecule, how many hydrogens do I have? 2. How many oxygens do I have? 1. So as it's written right now, this equation does not obey the law of conservation of mass. I do not have the same amount of oxygens on both sides. Even though my hydrogens are good, this is not a balanced equation. So now what we're going to do is we're going to start to mess with the coefficients. Before we do that, I want to make a note down here at the bottom. This word in here is cannot, capitalized. You cannot, and I see students do this all the time, change the subscripts. Because I know it doesn't feel like we're actually doing the chemistry right now, because it's a lot of just chemical equations on paper. But changing the subscripts to make things more convenient, while it would work, for example, if I went down here and I said I have H2 plus I have O2, if I just went and said, okay, well, I've got H2O2, I mean, that would work, right? Like I've got 2 hydrogens, I got 2 hydrogens, I got 2 oxygens, I got 2 oxygens, we're good. But if you actually go to the lab and you mix hydrogen and oxygen, it doesn't make H2O2, it makes H2O. These are fundamentally different compounds. H2O is water. You go to the tap in this part of the world, you drink it safely. There's no issues. H2O2 is hydrogen peroxide. Does anyone know what hydrogen peroxide is and what it's used for? Hands up if you've ever got a scrape on your knee, on your hand, and some adult in your life has put some liquid on it that fizzed and burned like crazy. What they put on you was hydrogen peroxide. Hydrogen peroxide is designed to kill basically anything it touches. Hydrogen peroxide, anyone who did that to you, they're trying to disinfect you because you get your scrape, you know, your skin's open, there's a little bit of blood there. So anything that might be getting into you, they want to, microbes from the world, they want to kill those. But unfortunately in the process, the reason it hurts you is because it kills the skin around the open cuts. It's doing as much damage to you as it's doing to those microbes. Fortunately, they're a lot smaller than you, so it just stings a little bit on you. On them, it rips them apart. Hydrogen peroxide is actually the most dangerous thing we have in the chemical storage room here at Abyssinia. If you go to the grocery store and you buy hydrogen peroxide, it will likely only say 3%. It says 3% on the bottle because that means the bottle is 3% hydrogen peroxide and 97% water. Because you don't need more than 3% hydrogen peroxide to clean out a cut. In the lab, we have, it's either 30% or 40% hydrogen peroxide, which is still 60 or 70% water. And it is the single most dangerous compound we have. It will wipe out a human being, no problem. It's very dangerous. And a little bit on, and I've done this before, a little bit on your skin will actually, like if I have no cuts, if I touch this stuff, it actually will turn your hand white because it's killing that top layer of skin. And so if you allow it to continue to interact, it'll just kind of burn its way right through whatever it touches. It's nasty stuff. And you don't feel it, is the other thing. I've done this, I've had students do this before. I don't do it anymore. But I've had students, I made bubbles out of this stuff. And I'll do it. I'll do this demo for you guys. And at that point, in the future, in about 3 weeks, it might be the first week of April after we come back, I will ask any of you, does anyone want to touch the bubbles? And if you have forgotten this discussion and you agreed to touch the bubbles, you will get a chemical burn. If you'd like, I will do it. I'll demonstrate it for you. And you can do it yourself. And you can see what a chemical burn actually feels like for something like this. But hydrogen, so that's why changing the subscript is, I mean, here it looks like nothing. I'm changing a number. But in the lab, in the real world, and chemistry is the closest thing to the real world that you're going to get as a science in high school, changing that subscript is wildly dangerous. It changes the chemicals. From something that you can drink to something that will happily kill you in an instant. And I'm not even exaggerating here. Hydrogen peroxide is wildly dangerous. So now we're going to go through and we're going to change these coefficients. I'm going to give you an example. I'm going to give you some tips. And then I'm going to show you a whole bunch of exercises of how this works out. So my hydrogens are good. I've got 2 on the left, 2 on the right. The hydrogens are obeying the law of conservation of mass. So let's go ahead and look at the oxygens. I have 2 oxygens here. I've got 1 here. What could we do to the coefficient in front of the water molecule to make it so that I have the same number of oxygens on the left as on the right? I could put a 2 here. If I put a 2 out front, how many oxygen atoms do I have now? I have 2. I have 2 molecules of water. Each water molecule has 1 oxygen. So now I've got 2 times 1 is 2 oxygens. But putting that 2 out front means I've also changed the hydrogens, right? Because the hydrogens are part of this molecule. So now how many hydrogen atoms do I have? I got 4. 2 groups of 2 means now I've got 4 hydrogens. So even though the oxygens are balanced now, I've got a problem with the hydrogens. So now we jump back to the other side. But over here, this is nice because my hydrogens and oxygens are separate molecules. Changing this coefficient doesn't change my oxygens at all. It's just going to bump up my number of hydrogens. So what could I do here out front to give me the same number of hydrogens here as over here? If I put a 2 here, 2 groups of 2 is 4 hydrogens. And now if I go ahead and look, I've got H4, I've got H4, O2, and I've got O2. Now this thing is balanced. It obeys the law of conservation of mass. And this is actually a really neat reaction. We are not allowed to do this reaction here at Abyssinian because this is actually quite a dangerous reaction. Hands up if you've ever heard of the Hindenburg. You've heard of the Hindenburg? Can you describe it at all, or you just know that it was a thing that existed? It was the blimp that blew up. So I'll show you a quick picture of the Hindenburg, because why not? It's probably going to be a picture of my family that shows up first. That's not the Hindenburg. It's before my son was born. Come on, computer. Figure yourself out. Here we go. So that guy right there is the Hindenburg. Back at the beginning of the history of flight, people were like, we can fly now. Airplanes are a thing, but airplanes were still wildly dangerous because people were still trying to figure them out. So people were like, there's other ways to float through the air. Let's use balloons. Okay, cool. So they made balloons. They started with the hot air balloon, and they're like, well, hot air balloons are kind of small. It's hard to control them. So let's make the balloon huge and put a motor on it and fly it through the air and actually be able to steer the thing. And so they invented the blimp. Or the Zeppelin. The Hindenburg is a Zeppelin, and you want to make these things so they're strong. And so what they did was they had a wire frame, and they covered it with a thin aluminum shell. I think pretty sure it was aluminum, thin aluminum shell. So they've got lots of metal here, and metal rubbing on metal. And then they said, okay, well, to make this thing float, we need to fill it with a gas that's lighter than air that's easy to make. So when I say a gas that's that's lighter than air, your first thought goes to helium. Helium's hard to produce. There's not a lot of it on our planet. Even though we use it, we waste it for balloons. We don't actually have a lot of it on our planet, comparatively speaking. But something that's really easy to produce is hydrogen. You just need to boil a bunch of, well, not boil. You need to electrically split water. You can make hydrogen gas and oxygen gas. I've done it. It's not hard to do. You just need the right equipment. You can produce limitless hydrogen. As long as there's water on the planet, hydrogen is a fuel source. It's great. And it's lighter than air. Sweet. So we're going to take the balloon, we're going to fill it up with hydrogen gas. It will float. We fly the thing around. Unfortunately, they put this thing inside a metal shell on a metal shell. When metal rubs on metal, what does it do? It sparks. Hydrogen gas is insanely flammable, especially in the presence of oxygen. Oxygen on its own isn't flammable, but oxygen allows other things to be flammable. Atmosphere is full of oxygen. That balloon was full of hydrogen. When a spark occurred and the shell ripped a little bit, the hydrogen gas inside was allowed to mix with the oxygen in the air outside. The spark ignited that explosion. Now, we at Abyssinian, when our school was built, we were not built. Yes, sir. Yes, they did. World War I. World War I. Between World War I and World War II, we figured out planes. Yes, until we figured out planes. And then planes became way safer. Also quicker, but I digress. W.J. Mowat, early high school, one of the earlier high schools built in Abbotsford, has hydrogen tanks and oxygen tanks built into their science prep room. They have this stuff. And so they used to do it at Mowat. They're not allowed to do it anymore because people complained. What they would do is they would take a balloon, they'd fill it up with hydrogen gas the same way you'd fill it up with helium. That hydrogen, actually what they would do is they fill up a garbage bag. And then they tie the garbage bag off, make a really big balloon. And then they'd take it into the middle of their football field. And they'd tie it to the ground and they let it sit there. And then a teacher would come along and he'd poke it with a flaming stick. The same explosion that happened with the Hindenburg would happen in the field outside W.J. Mowat. It's much smaller because it's a garbage bag, not a blimp. But it's a garbage bag full of hydrogen. So you poke it with a flaming stick, it's allowed to then react with all the oxygen in the air. The thing goes boom. The reason they're not allowed to do it anymore, because the entire neighborhood around Mowat complained. Because that explosion would shake the windows on all the homes around Mowat. It's a massive explosion. But what does it produce? It produces water. So this is two gases, boom, windows shake, and a fine mist kind of just rains to the ground. Now, it's important to recognize, because I'm a math teacher, I want to make a comment here. It's important to recognize that there are no units on these numbers. I care about units. As a math teacher, physics teacher, and chemistry teacher, I care about units. And when I say units, I mean things like the number of atoms, or milliliters, or liters, or like the how you measure something. There are no units on these coefficients out front here. And so these proportions can scale up. So what this means is, yeah, sure, I could have 2 molecules of hydrogen reacting with 1 molecule when there is no coefficient, it's a 1. 1 molecule of oxygen produces 2 molecules of water. But I could also scale this thing up. I could say, this is 2 liters of hydrogen gas. I could take a pop bottle full of hydrogen gas, a 2-liter pop bottle. I could allow it to react with 1 liter of oxygen gas, and it would make for you a 2 liter of water. I mean, there's an explosion in the middle, but you'd get a measurable amount. You get a pop bottle of water that you could then collect. And that is the beauty of going through the process of balancing these things, because then you can take this balanced equation and say, this is what I think it will do. And you can walk that into the lab and you can actually do it with the chemicals that we have. You can get 2 liters of a liquid. You can get 1 liter of a liquid. You can allow them to mix, and you can see, normally you'd think, okay, well, 2 liters and 1 liter should produce 3 liters. But according to this, 2 liters of this gas and 1 liter of this gas will actually make 2 liters of this liquid. And you can go ahead and you can actually try it and see if what you predicted worked. And that's a big part of what you're going to do in Chem 11. It's a cool class. It depends on who's teaching it. The first year I taught it, we didn't do any labs because I was scared. Not anymore. So it can be a really cool class. So, some balancing tips. Here we go. Let's write these down and do some examples. You will not have any homework today from me. You betcha. You're not going to have any homework from me today because we'll spend the bulk of class doing it tomorrow, and I didn't give any homework to my other block. I want to keep you guys at the same pace. But let's talk about some tips. So, when you go ahead, and I'm going to task you with this, I'm going to give you probably 200 questions over the next 3 or 4 days to practice balancing. Because the only way you get good is by doing a crap ton of this stuff. So, I'm going to give you a lot to do. Yes, sir. Oh, I left a blank. You cannot change the number of subscripts to balance the number of atoms, is the word that should go in there. I think I said it, but I didn't write it down. So, when you go ahead and you change these coefficients, it's going to involve some trial and error. As a math teacher, I hate guess and check. It's the worst way to do things. Unfortunately, in balancing chemical reactions, a large part of it is guess and check. It's trial and error, seeing if the changes that you make work the way you want them to work. So, because you've got trial and error in here, my recommendation, first of all, is the tools you choose to use. Use a pencil. You can erase a pencil. But even better than that, when you're doing these balancing exercises, the better tool to use is the whiteboard. I've got 9 of them. There are 9 whiteboards in this class. Use them. I will force you to over the next week or so. As you're practicing these things, I'll get you guys up on the whiteboard. When you're now, some practical bits about the equations themselves. Usually when you balance these things, you're going to start with the furthest left element. And you're going to work left to right. Usually. Didn't quite work out up here because the hydrogens were already balanced, so then we had to move to the oxygens. But you'd start just like you would when you read these things. In Canada, most of the English-speaking world, we read left to right. So that's how you're going to attack these things, left to right. Start with the furthest left element and work your way right. If you have hydrogen and oxygen are going to be the biggest issue you have is balancing the hydrogens and the oxygens. If they appear in several different formulas, if they appear in more than one place on each side, leave them until last. And then of those two, hydrogen is usually the absolute last one. Leave oxygen and hydrogen, change everything you can change, and then at the very end, go back and see if you can address the oxygens and the hydrogens. Oxygens first, hydrogen's absolute last. I'm going to put a star here for this last point here, because sometimes I give this tip and sometimes I don't. I have found that often students, this last tip actually makes things worse for students. So I'm just going to leave it blank there for a little bit. And then there will be a few of you likely who will be like, I'm really comfortable with this. I want to see what that last tip was. It's a bit of a shortcut. It does make things more complicated for you to store in your head, but it is a teensy bit of a shortcut. For those of you who are interested, I'll show it to you later. I'm going to add another tip down here at the bottom. It's not going to make a lot of sense right now, but I'll give a bunch of examples and I'll show you what I mean. If odd amounts of oxygen cause problems, and I will show you what I mean by this statement. If you have odd amounts of oxygen and they're causing you problems, the reason that they're causing you problem is the oddness of it all. How do you, in math, how do you make something not odd? Sorry? That's one way to do it. That's not what we're going to do. There's another way to do it. Sorry? Yes, that is the technique that we're going to use. If odd amounts of things of oxygens are causing you problems, double, multiply by 2, everything you've already done. And it will solve your problems for you. I will show you an example of what I mean. Now, these are not the only tips that exist for balancing. Okay? These are the intro tips that I'm giving you. As you go on and do more of these things, there are other techniques that I can introduce. One of them being this blank, this section that I'm leaving blank here. For those of you who are ready for it and interested in it, I can show you this technique. There is a third technique that I can show you. I had never actually seen it before until I taught a girl from Spain a couple years ago. She has since gone home, but she was here. She was from Spain, and over there in Spain, they teach it's quite an interesting technique, but it requires some pretty significant math skills that not all of you perhaps are interested in learning. If you are a strong, like really strong math student, I will happily show you those techniques. They're really cool. It's a lot of work, but they will always work every time. So if you're interested in that third kind of mathy technique, let me know. I'll show it to you individually. But as a general rule for the stuff that I'm going to give you at this stage, these are a good place to start. I'll do a couple examples, and then the bell's going to go for lunch. And you're not going to have any homework for me today. Let's take a look at some of these. So, here we go. Balancing examples. Does that one work? Yeah, okay, here we go. Let's do the first one. I've got K. K is on its own. It's a metal. It's not going to be bonded with anything. It's going to react with O2. It's the same process that we looked at with magnesium. This is the rusting of potassium metal. So K plus O2, it's going to react to form K2O. Is that balanced? Well, let's count. I've got K's and I've got O's. I've got K's and I've got O's. How many K's are on the left? 1. How many O's are on the left? 2. Cool. On the right, how many K's do I have? 2. How many O's do I have? 1. So let's go ahead and figure this out. As a general rule, one of the things I said was generally what we want to do is start left to right and leave oxygen till the end. So let's go balance our potassiums first. What could I do to the K so that the k's on the left equal the k's on the right. Toss a 2 out front. Okay? If I do that, putting a 2 out front here is just going to make the number of potassiums on the left equal to 2. 2 times 1 is 2. My k's are good. Let's go look at the oxygens. Okay, well, I've got O2 on the left. I've got K2O on the right. So let's balance the oxygens. What am I going to have to put in front of the K2O? I have to put a 2 there. Because 2 times the 1 oxygen is going to give me 2 oxygens, and I recount. But when you change a coefficient, you have to recount everything. So Angel, what's the problem? Sorry? Yeah, now I have to multiply these. How many potassiums do I have over here now? 4. So now I've got a problem. My oxygens are good now, but now I've unbalanced my potassiums. So let's go back and fix the potassiums. Instead of putting a 2 here, what could I change this to give me the right number of potassiums? Instead of a 2, I could make this a 4. And now, instead of having 2 potassiums here, how many potassiums do I have? I have 4. And so now I've got 4 potassiums, 2 oxygens, 2 oxygens. This thing is now balanced, and this is why this right here is why I said to use a pencil. Because now what I've got to do is I've got to go ahead and rewrite this thing. So the fully balanced equation is going to be 4K plus O2 arrow 2 K2O. This is now the fully balanced equation. Let's go do another one that looks slightly more interesting. One of the things that I'm going to get you guys, actually, you know what? No, I'm not. Bell's going to go here in a second. We'll move on to example 2 tomorrow. You have no homework. Welcome to balancing. We'll do a lot of it over the next couple days. When the bell goes, you may also go. Have a great day. We'll see you tomorrow. You should have actually gone already.